When the heavy perplexity pipeline fails, a simple, high-dimensional linear classifier takes over, cleanly separating AI text from human text, with an 85% accuracy rate per sentence. The industry standard for detecting AI-generated text relies on feeding content back into large language models. These massive networks calculate text perplexity, scoring the probability of every individual word choice across billions of parameters. But in practice, perplexity-based detection breaks down. Research shows it frequently produces false positives, fails to generalize across different models, and creates unsustainable inference costs just to verify a simple text file. Look at this technical schematic. The architecture driving this result uses no deep learning. It pairs a basic term frequency inverse document frequency matrix, a bag of words model, directly with a linear support vector classifier. Compare the computational footprints. The linear classifier requires no foundation model weights, no expensive GPU clusters, and no API calls. It operates entirely on raw, unformatted text. While commercial services struggle with erratic thresholds and high overhead, this deterministic pipeline matches their accuracy using 1990s mathematics. It achieves a reliable signal without the billions of dollars in infrastructure. The central engineering challenge here is scale. To prove this architecture works, we have to scale a classical machine learning detector to match commercial checkers without incurring any server-side computing or API costs. Executing this requires 3 mandatory phases: synthetic data generation to build the training set, support vector machine training to draw the mathematical boundaries, and client-side ensembling for actual deployment. The timeline of the training data dictates everything. The baseline human texts must be sourced exclusively from publications prior to 2022 to guarantee they are free from pre-existing AI contamination. AIGC detection relies on identifying rigid statistical fingerprints, a pattern matching problem that sidesteps the need for deep semantic understanding. We establish the bedrock of the training set by sampling nearly 10,000 multi-thousand character human texts. This volume guarantees a diverse baseline of uncontaminated human-authored syntax. To create the AI dataset, we use a strict mirroring protocol. We summarize the human texts, then feed those summaries back into language models, prompting them to generate structurally and thematically identical counterpart articles. This schematic tracks 10,000 human data points, flowing into 7 foundation models, from Gemini to DeepSeek. To bypass exorbitant API costs, we batch massive high-context prompts. This forces the LLMs to generate high volumes of synthetic content per single call. Because every synthetic output is tied directly to a human original, variables like genre, length, and subject matter are completely normalized across the entire corpus. By perfectly mirroring the human baseline, this dataset mathematically isolates the exact variable we are looking for, the pure statistical word choice biases inherent to LLM generation. The pre-processing step strips the articles down to their structural components. We segment the full text by sentence and filter out all non-alphanumeric noise to isolate the raw vocabulary. We then transform these raw sentences into a high-dimensional TF-IDF sparse matrix, converting word frequency into mathematical coordinates. Here we see the matrix visualization. The linear support vector classifier draws a mathematical boundary, a hyperplane, slicing through the coordinate space to separate human and AI data. These classifiers yield an 85% accuracy rate per sentence and F1 scores exceeding 80%. Testing a BERT-based model did provide marginal accuracy gains. However, the associated GPU inference time rendered it completely non-viable for a zero-cost local deployment. The linear classifier won out on sheer efficiency. Finding an 85% signal at the individual sentence level means that when we aggregate those scores across a full-length document, we achieve near absolute statistical confidence in the result. The final deployment constraint mandates a strict serverless philosophy. The model must run natively in the user's browser, using WebAssembly and JavaScript. To make the file size browser compatible, we execute aggressive feature pruning. Capping the model at 500,000 features compresses the entire payload down to a 38-megabyte JSON file. Discarding features down to lower thresholds caused catastrophic false positives. Holding the limit at 500,000 features resulted in a negligible 1% accuracy drop, maintaining the integrity of the detector. This schematic maps the noise reduction strategy. To stabilize the pruned model, a single sentence passes through 7 parallel binary classifiers. A positive AI flag triggers only if 2 or more classifiers return a positive hit. We ran this ensemble against a dataset of 10,000 articles found in the wild. At a 70% confidence threshold, the false positive rate dropped to less than 0.01%. Stripping away the overhead of deep learning in favor of a tightly pruned, ensembled classical model delivers a highly optimal, production-ready architecture. If these binary classifiers separate human from AI text with near-perfect accuracy, a new hypothesis emerges. Can an 8-class classical model successfully identify the specific AI model that generated a text? The experiment failed immediately. Multi-class accuracy collapsed to a near-random 50%. On this topological map of the latent space, the human data points remain cleanly separated in their own distinct, isolated cluster. But the synthetic data tells a different story. The 7 AI clusters hopelessly overlap, violently collapsing into a single, indistinguishable central node. The root cause of this collapse is cross-distillation. Because top-tier foundation models are heavily trained on each other's outputs, their structures are actively converging onto the exact same probabilistic vocabulary. The pipeline reveals a stark dichotomy. LLM word choice fingerprints are so loud that classical algorithms can instantly isolate them from human text, yet they are so identical to each other that they cannot be told apart. This visual represents model monoculture. The world's most advanced foundation models are all learning to write with the exact same rigid, predictable conformity. True intelligence and creative capacity require variance. This highly predictable statistical output lacks the depth required for original human-level creation. This leaves us with an unresolved problem. We have to question what happens to the integrity of the internet ecosystem when the digital landscape is flooded by this single, mathematically homogeneous voice. Classical machine learning can accurately map the boundary between human and AI text today, but soon that boundary may be the only meaningful distinction we have left. Synthetic Labs. From research paper to working prototype.